So this presentation will be about energy. The study of energy in chemical systems is called thermochemistry. The study of moving energy around in general is called thermodynamics, meaning heat energy, because that's what thermo is. So lesson objectives: we'll define kinetic and potential energy, we'll identify forms of kinetic and potential energy, we'll identify chemical and physical energy changes, and finally, we will define heat, thermal energy, and temperature. We can put energy into two categories: kinetic and potential energy. Kinetic energy is the energy of movement. It applies to any moving object or particle. So we're talking electrons all the way up through planets. Kinetic energy applies to. It is equal to 1/2 mass times velocity squared. So 1/2 mv squared. Heavier objects in motion have more kinetic energy than lighter objects in motion, going at the same speed. Potential energy is stored energy. Classic examples include things at altitude, for example, a ball on an incline, books on a high bookshelf, or paint cans on ladders. It can also refer to energy stored in chemical bonds. All matter that has bonds contains potential energy. And finally, intermolecular forces can have potential energy. We don't know what intermolecular forces are yet, so here we go. They're electrostatic attractions between molecules. What is an electrostatic attraction? Think of the shock that you get when you shuffle your sneakers on carpet and then you touch a metal door. Now, we have a nice GIF here, or GIF if you prefer, that illustrates the difference between kinetic and potential energy on the right. Note that the definition of kinetic energy does not work if there is not a GIF. Why? Because you can't show it moving. I guess you could add little lines, which we actually do in a later slide, but this looks better. Okay, so now we know the difference between kinetic and potential energy. Let's try classifying things. Classify the following as having kinetic or potential energy: a car parked on top of a hill, a traveling car, gasoline, and burning gasoline. And I've got the definitions in simplified form in the bottom right-hand corner there. So I want you to pause and think these through and label them as kinetic versus potential. Okay, so a car parked on top of a hill is not moving. It's at the top of a hill, so it could roll down the hill. Therefore, it has stored or potential energy. A traveling car is moving, and therefore it is kinetic energy. Gasoline can be burned to liberate energy, but it's not currently liberating energy, so it contains potential energy stored in the bonds. And finally, burning gasoline is having the bond energy liberated, which is what causes heat to be released, right? When you burn something, it heats things up. The particles start moving faster, and therefore this is kinetic energy. All right, so chemical change involves making new compounds, and a physical change can be returned to the same state without a chemical reaction. So let's think through some examples that we may remember from before. Chemical change is something like cooking toast. You change the bread irrevocably. It's a new compound when you toast it. Physical change would be like melting dry ice, or subliming dry ice, actually. All right, so let's practice these ideas. Let's talk about chemical versus physical energy changes. Classify the following as chemical or physical energy changes. Waves crashing on the seashore. So is that physical or chemical? Burning candles, cold packs that you crack to activate, freezing water, and cooking an egg. Take a pause, try to figure these out. So waves crashing on the seashore is a physical change. Waves are transferring energy. It is a kinetic type of energy. Burning candles, sorry. Interestingly enough, this is actually both a chemical and a physical change. If you've ever looked at a candle while it is burning, The wax is melted around the wick, and the wick is pulling stuff in. Wax must be in a gaseous state before it will burn. So you're melting and evaporating. Both of those are physical. But the burning itself is a chemical reaction. You're making CO2 and water, and you can never get it back to the form of wax. Cold packs the crack open to activate. Cracking it open is a physical change, as is the, and I put it in quotes here, reaction. You're actually just taking something out of solution. It's still the same molecule, it's just no longer dissolved. Freezing water is a physical change. It's still water if it's an ice cube. And finally, cooking an egg is a chemical change. You added heat and you changed the order of the proteins. So this brings us to thermodynamics. It's the study of energy transfers in a system, both how much and how it is transferred. Thermochemistry specifically refers to the heat absorbed during chemical and physical changes. So thermochemistry is what we're going to be dealing with in this chapter. Thermal energy is the kinetic energy of random motion of molecules. So literally all molecules, if they're not at absolute zero, are vibrating all the time. If you've got gas, it's a free agent. It's going wherever it wants. Okay, temperature is the root mean square average of kinetic energy. Don't worry so much about root mean square average, and remember that it is proportional to kinetic energy. This is a quantification of thermal energy. So if it's hotter, the temperature is higher and the thermal energy is higher. If the temperature is low, that means the kinetic energy is low and the thermal energy is, yes, you guessed it, low. Heat is the transfer of thermal energy from two bodies at different temperatures. Now, at the very bottom here, we have an illustration of that process, and it will allow us to access those other two definitions as well. So you notice that there's little lines around each molecule, and the amount of lines indicates how fast the thing is moving. So over here in A, we have hot or high and low temperature. At the high temperature, the molecules are moving pretty fast. At the low temperature, they're moving much slower. As you put them in thermal contact with each other, so that's where you merge those boxes, the hot molecules are going to transfer energy to the low energy molecules. And as that energy transfer takes place, you eventually reach equilibrium where both temperatures on both sides are equal. So we can transfer heat from one side to the other. It is thermal energy that you're transferring, and you can have things at different temperatures, but once you reach equilibrium, because you've got good thermal contact, there is no difference in temperature at all. Now, one final thing. This process of transferring heat takes place every day, all the time. In your body, in engines, in outer space, in hurricanes. This is why thermodynamics is a powerful tool in our chemistry skill set. It applies to all energy transfers. To summarize, kinetic energy is the energy of movement. Potential energy is stored energy. A chemical change involves making new compounds, where a physical change can be returned to the same state without chemical reaction. Thermal energy is the kinetic energy of the random motion of molecules. Temperature is the root mean square average of kinetic energy, and it quantifies thermal energy. So high temperature means more kinetic energy, low temperature means less kinetic energy. And finally, heat transfer of thermal energy between two bodies at different temperatures. So when you heat something up, you are transferring energy.